Today's video is about how to keep track of indices in Tensors. This video got inspired by the video series I'm currently watching on Tensors. This video series is excellent. Like, it's really good source. And one of the very first videos, I noticed that I really don't understand how those indices work, what belongs to what we're summing over, and I decided to set some time aside and make sure I understand. And also some people in comments were asking if someone could please explain this. So this is my attempt at explaining how to keep track of indices in Tensors. So as you can see, I wrote some stuff down to keep this video as short as I can. So suppose we have a linear transformation represented by this set of linear equations. So we want to get to some new basis represented by these basis vectors, E tilde. So we want to go from the blue basis vectors to new E tilde red basis vectors. And those yellow indices represent the coordinates of the vectors represented in the new coordinate system. So basically, how much of each of the component of the how much of each of the basis vectors goes into the components of the new basis vectors. And then we take these indices and put them into a matrix so we can do some math with it. There is matrix notation, and there is also a summation notation, which seems a bit confusing at first, but it comes in really handy when you go above 3 dimensions, where you could not just easily write the matrix for those indices. And so we have two cases, forward transformation and backward transformation. So let's look at how these indices were put together. Okay, so remember from linear algebra, we have a matrix represented, say, by some letter A, and it has a size of m by n. So m stands for m rows and n stands for n columns. So now keep in mind that the coefficients in those linear combinations equations above, like those yellow guys or the purple guys for the backward transformation here, so those coefficients form coordinate vectors, and coordinate vectors then become column vectors in a matrix once we put them in a matrix, like so. If you notice, these guys here, these guys here, like these purple vectors, become column vectors here. And the same goes for these guys. Okay, so that's one major point which actually helped me to understand the whole indices situation. So when we look at the indices of the coefficients, the J here stands for the rows and I stands for the columns. And the same goes for the B coefficients in the backward transform. Okay, so now let's take a closer look at the summation notation to make sure we understand this. So for example, let's take a look at the forward transformation. So this is this expression here. And let's suppose we have just 3 basis vectors that we are working in 3-dimensional space. So let's try to write them all down explicitly. So for the first vector, let's say we want to represent the first vector in our new basis. Actually, wait, it's not I, it's now 1. So this then equals to, we're summing over J. So f j sub 1 and EJ. Okay, so now let's expand these guys and see what we get. So for if j equals 1, we get f1, 1, and oh my goodness, I'm not doing the right thing. E1. And then we continue. So if j equals 2, we get f2. And we still have 1. So we still have, so the f sub 1, so this guy will become the first row entry. And this guy will become the first entry in the second row, and so forth. And we're still taking, we're still working with the first equation, so this is still going to be the first column. So therefore we have still ones here. Okay, so moving on, we get f3 sub 1, e3. And so if we keep writing these guys out, we get the following. Okay, if j equals 1, we get f1, 2, right? Because the first, we have the first row and the second column. Okay. So second row, second column. Third row, still second column. Come on. So still second column. Okay, now the third vector in the new coordinate system is going to look like this. Okay, so first row, third column, and second row, third column, and third row, and third column. Okay, so if we collect now all the coefficients into a matrix, we get the following, like turning the rows into columns. So these guys will become a column. Okay, so here we have it. It looks exactly like we had a couple slides ago, like this form. Or like this. Well, this is just for the general case for n vectors, so n rows and columns. And here we just have a special case for the three-dimensional space. Okay, so this is exactly what we've got above, and therefore we confirmed that this equation indeed gives us the matrix form back, just as we had earlier and on the first slide here. Okay, so this is it, guys. I hope that this was helpful. I definitely understood what the whole deal is with these indices and how to work with them, because they come up a lot when you go to study tensors further. There are things like Kronecker delta and Levi-Civita symbols, which have even more indices to keep track of, and this is the first step in understanding those. So I hope this was helpful, and I see you next time. Bye.